Hi, I'm Shinibali, and I work at Cruise as a quantum physicist. In this video, I'll walk you through the usage of Cruise toolset for optimally controlled state preparation of CAT qubits. For starters, let me explain what CAT qubits are. These are special kinds of superconducting qubits that have biased errors and are claimed to reduce the resource overhead for implementation of surface codes in the era of fault-tolerant quantum computing. A cat qubit is essentially composed of the superposition of two opposite states at once, such that the cat state can be in both 0 and 1 at the same time. And with this specific way of encoding quantum information, one can replace thousands of physical qubits with only several tens of cat qubits to enable building a logical qubit with reduced overhead. In this video, we'll focus on a special type of cat qubits termed as dissipative cats that are designed to be biased in favor of very large T1, that is the bit flip times between the 0 and the 1 state being of the order of several hundreds of milliseconds, while having a very short T2 star, that is the phase flip times of the order of microseconds. Given the motivation of having well-functioning cat qubits, let's understand the hardware setup that can create, manipulate, and then read out such dissipative cats, courtesy of Alice and Bob, a company based in France. In this adapted schematics, we see that the cat cavity colored in blue here is coupled to a resonator called buffer, shown in red, and the interaction between them is mediated through an asymmetrically threaded squid, ATS for short. It enables the pairwise exchange of photons from and to the cat cavity, while only a single photon is exchanged with the buffer. So by driving the buffer at a given amplitude, one populates the cat cavity with a photon count that is proportional to the drive amplitude. This engineered dissipation mechanism, where the two-photon loss rate of the cavity is much lower than the single photon loss rate of the buffer, helps in stabilizing the cat qubits. Upon the creation and the manipulation of the cat state, in the end, one can read out this cat state via a tomography apparatus shown in green over here. In the next video, we will dive deeper into the simulation of the tomography protocol for cat qubits. With this basic understanding of the hardware setup, let's dive into how we can simulate optimally controlled state preparation of cat qubits using our Cruise toolset. This is the Hamiltonian in the rotating wave approximation dictating the state preparation process in the combined reference frame of the cavity and the buffer. Here G2 is the coupling strength between the buffer and the cat cavity, and the associated electron operators reflects the pairwise exchange of photons between the cavity and the buffer. We also have self-Kerr terms for both the cavity and the buffer modes, another cross-Kerr coupling term between the buffer and the cavity. Then we apply a simple X drive to the buffer, which in turn populates the cat cavity, and a simple drive to the cat cavity to enable correction of the Kerr effects. We consider open system dynamics to account for dissipation via the loss operators corresponding to the buffer and the cavity. To build our digital twin simulator for the cat state, the first important step is to declare all the experimental parameters for a given hardware setup. We will discuss these parameters in more detail in the following steps. We will first set up our model where we instantiate a cat state class using the experimental obtained system parameters. For our multi-level cat state that we want to simulate efficiently, we declare its highest Fock level for its Hilbert dimension. And for the simplicity of the simulations, we consider operating at resonance mode, where the frequency of the cavity would be 0. We also provide the self-Kerr strength, the single photon loss rate kappa, 1 to the cat state class, and we declare a specific temperature of the bath that can be used to account for thermalization in the simulations. In a similar fashion, we declare the parameters corresponding to the 3-level buffer mode. And next, we declare the photon coupling and the cross-Kerr coupling terms between the buffer and the cavity. We also defined a X drive connected to the buffer and a curve correction drive connected to the cavity. With these individual components all in place, we instantiate the model Hamiltonian class that we want to simulate, where the subsystems are the buffer and the cavity. Then the couplings are the different couplings and the drive terms connected to these subsystems. And the open system dynamics is set to true by the Boolean flag Lindbladian. Next, we define a single instruction for both the drive channels connected to the buffer and the cavity by instantiating ideal square-shaped pulse envelopes. It's worth noticing that though optimal control of the drive pulses will result in desirable pulse shapes for a specific task, we initialize the pulse envelopes as square envelopes with physically motivated values for their amplitude and duration. In the case of the buffer drive, this amplitude dictates the photon number of the cat cavity, so we initialize it to achieve a targeted photon number. We also instantiate a simple generator which allows us to simulate the behavior of an ideal classical control electronic stack by neglecting its classical errors. Then we define a parameter map that maps all the components we have associated with the model, the generator, and the instructions. We then create an experiment object, naming it as the simulation, that takes into account the above parameter map, chooses a specific kind of different equation solver method, and its simulation resolution. Besides, we pre-compute the unitary propagators for numerical efficiency and later usage. To observe the population dynamics during the unoptimized state evolution, we defined a ground state of the combined buffer and cat modes and let it evolve for the sequence of instructions that we defined earlier. So the legend in the right in this plot is arranged in descending order of population from top to the bottom, with the first index corresponding to the 3-level buffer and the second index corresponding to the Fock level of the cavity. As expected, the ground state population with the label 00 goes down as a function of time, and the higher Fock states of the cavity starts getting populated. However, for the given Hamiltonian, the desired cavity Fock level for occupation are the even Fock levels. That should result in an even cat state. Later during optimal control of drive pulses, we will see how this can be achieved. We will also show the Wigner visualization of the unoptimized cat state preparation in this video, where a cat state gets squeezed out of vacuum. Isn't that fun? Okay, so the next plot is for the expectation value of the cat cavity. One should expect it to saturate to the targeted photon number, which was considered to be 2.25 for our simulation. This was, however, not achieved during this unoptimized state preparation process, so we will also revisit this issue after optimally controlled state preparation. So to start the open loop optimal control process, we now visualize how an ideal even cat state should look like in the Wigner phase space for a given target photon number. Next, we will use industry standard GRAPE optimization method, which stands for Gradient Ascent Pulse Engineering. And for this, we define a new drive instruction with the PWL's pulse, piecewise linear pulse envelope connected to the buffer and the cavity drives, which can be optimized for achieving the target cat state. Then we also set the parameter map with this new drive instruction and declare which parameters we want to target for the optimal control. So we allow the modulation of the in-phase components of the drives. And we build a new experiment object, pre-compute the propagators, and then we instantiate the cruise optimal control class by providing a goal function which we want to minimize. And in this case, it is the infidelity measure of the density matrix overlap between the ideal state and the simulated outcome, spanning over the subspace of the buffer and the cavity. We choose LBFGS, which is a gradient-based optimization algorithm from the SciPy library for this specific optimization task. And after executing it, We'll look at the final value of the infidelity parameter, which turns out to be 0.42. The corresponding pulse for the drive on the buffer looks like this plot over here as a function of time, and the drive on the cat cavity looks like this pulse over here. The population dynamics of the optimized state evolution now shows that the top 3 most populated Fock levels of the cat cavity are even-numbered Fock levels, as was desired. And the optimized cat qubit looks like this Wigner plot over here. Expectation value of this cat cavity has saturated to 2.16, which is almost 96% of the targeted photon number 2.25. This is a substantial improvement compared to the state preparation with unoptimized drive pulses. One might have noticed that the state preparation fidelity is extremely low even after optimal control process, which led us to investigate the underlying cause. And we pinned it down to 2 important parameters of the hardware. One of them is the cavity and the buffer coupling parameter G2, and the other one being the single photon loss rate of the cavity called kappa 1. So these contour maps here show the state preparation fidelity as a function of G2 and kappa 1. The red star in these diagrams denotes the G2 and the kappa 1 value for the Allison Bob hardware prototype from the year of 2020. We explored the phase space by increasing the value of G2 and decreasing the value of kappa 1 compared to their 2020 hardware versions. The plot on the left shows the state preparation fidelity before using Cruise optimal control software, and the plot on the right shows the same after using the optimal control software. One can see obvious improvements in the state preparation fidelity due to the optimal control protocol by referring to the color legend on the right. Before optimal control, fidelities tend to be of lower value, depicting mostly dark green and bluish regions in the phase space. And after optimal control, the contour depicts higher fidelity regions with lighter green and yellow colors. In some cases of high G2 and low kappa 1 values, it even surpasses 98% fidelity. This investigation led us to realize that better state preparation fidelity requires larger cat and buffer coupling strength G2 and highly reduced single photon loss rate kappa 1. With Allison Bob's version of hardware parameters from 2020 that we have used in our main simulation, the small G2 and the large kappa 1 led to poor state preparation fidelity, indicating severe hardware limitations that cannot be overcome through the usage of optimal control software alone. With this knowledge of optimally controlled state preparation of cat qubits, we will conclude this video and hope that in the future, better hardware with higher values of the coupling G2 and lower single photon loss rate of kappa 1 will be available so that we can achieve higher state preparation fidelity. In the next video, we will show the simulations of Wigner tomography protocol to read out the cat states. Thanks for listening.